Welcome you all to the Research Spark YouTube channel. So this is the third session of the second unit, analysis of continuous time, signal and system. Here is the outline of this session. So mostly we are going to talk about the Laplace transform followed by the inverse Laplace and the region of convergence. So first thing is that what do you mean by the Laplace transform? So again, the Laplace transform is being used to convert any signals from time domain to the frequency domain or S domain. So S is, it is defined as the J of omega. So now we are going to use the S plane. So like here, if you wanted to convert the time to frequency domain, that is if you wanted to take the Laplace transform of any function f x of t, then you can use this formula like L of f of t is equal to of e to the power minus st into f of t dt. So simply multiply by e to the power minus st with that particular function f of t and integrate it over 0 to infinity with respect to dt, and you will get the Laplace transform. So as for example, let's consider the Laplace transform of 1, that is the f of t is equal to 1. So now just replace the f of t with the 1. So you will get the Laplace transform will be equal to the 0 to infinity integration e to the power minus st into 1 into dt. So now since the integration of exponential is something e to the power minus of st divided by minus of s, and now just put the limit from 0 to infinity. If you will put the limit, then e to the power minus of infinity. So since e to the power minus infinity, so it will be 1 divided by infinity and will be equal to 0, and minus of e to the power, like if you will put the 0, then e to the this will be your 1 e to the power 0 is equal to 1 divided by minus of s. So finally we'll get the Laplace transform of function f of t is equal to 1. That will be the Laplace transform will be 1 by s. So it will be defined for s greater than 0 only. So now, similarly, like consider the another popular example, that is f of t is equal to e to the power of at. So again, we'll do the same process. So you must try to do the some more exercises. I am just taking the only this one, that is popular example. So now how will you do? So just replace your f of t with the particular function, that is e to the power at. So now you will have the e to the power minus at into e to the power minus st and into dt, and integrate it over 0 to infinity. So now exponential base you can take it common and you will get the a minus s into t and the dt. So again the exponential, if you do the integration, so since e to the power minus st is divided by minus of s, so you know the same techniques use, and you will get the something integration and put the limit, that is 0 to infinity, and finally you will get the value 1 divided by s of minus a. So the Laplace transform of e to the power at will be equal to 1 divided by s minus a. Just check the process, and if you have any problem, please drop the comments. We'll reply accordingly. So s will be again defined by greater than a, because s of minus a, if you make it 0, then it will be your a. So just it should be defined greater than a. So here is some summary. The Laplace transform of 1 is 1 by s, e to the power at is 1 by s minus a. T will be 1 by s square, t or any t to the power n. It can be written as a factorial of n divided by s to the power of n plus 1. So you can use this formula as well. Otherwise, you can just use this technique and find out. Also, you can find out the Laplace transform of sinusoidal signal or cosine signal. So how will you find out? Simply convert using the Euler's formula. You can just convert sine or cosine into exponential. Like cosine will be written as 1 by twice into exponential of j omega t plus e to the exponential of minus j omega t. Like that you can write, and then you can take the Laplace transform of exponential as we have discussed in the previous slide, and then you can find out the final Laplace transform of these sinusoidal or cosine functions. So similarly, you can find out the Laplace transform of any functions. Now inverse Laplace transform. Simply inverse Laplace, again it means that we are converting back from S domain to the time domain. So that will be the inverse Laplace transform. And how can you find out? So you can either you can use the standard transform pairs, like if you remember the Laplace transform of particular functions, then you can use that technique. Otherwise you can use the partial fraction, that is decomposition, for complex rational functions. So let's consider here, for example, also like if you wanted to find out the inverse Laplace transform, then you must remember the some the Laplace transform of particular functions. If you remember, then it will be very easy for you to find out the inverse Laplace transform of particular function. Let's consider the example of f of s is equal to 2 divided by s into s plus 3. So now we'll use a partial fraction, and just we can write it a divided by s plus b divided by s plus 3, and then find out the values of a and b. Why is it so? Because we know the Laplace transform something divided by s and something divided by s plus a or any quantities. So by finding the values of a and b, you can write the final values will be a is equal to 2 by 3 and b is equal to 2 by 3. So now we have the 2 divided by s plus s into s plus 3 is equal to 2 by 3 divided by s minus 2 by 3 divided by s plus 3. So now if we remember, Laplace transform of step function is 1 by s. So here again the and also Laplace transform of 1 divided by s minus a, inverse Laplace transform will be equal to d to the power minus s minus a into t. So use this technique. So inverse Laplace will be your 2 by 3 divided by s. So that will be 2 by 3 into 1, because 1 by s having the inverse Laplace transform is 1. 2 by 3 is constant and common, so take it out. Similarly, 2 by 3 again in the another term you can take it out, and it 1 divided by s plus 3. So this will be e to the power minus 3 into t, since a is equal to 3. So this will be your final inverse Laplace transform. So likewise, you can find out the inverse Laplace transform for any function, any f of s. Some examples: inverse Laplace transform for 1 by s is 1 divided by s minus a is e to the power at, and cosine you can see check the other functions as well. So just check, if you remember these data, then it will be easier for you to find out the inverse Laplace transform of any function. Now, what do you mean by the reason of convergence, that is ROC? So ROC of the Laplace transform is the set of values of S, or the complex frequency for which the Laplace transform integral converges. Or for a function f of t, its Laplace transform, you can find the f of s is equal to 0 to infinity to the power minus st f t dt. So the integral is valid only for the certain values of s. So it will not be valid for all the values. So whatever the values it will be defined, that is called as the RC, or the region of convergence. So for exponential function, the region of convergence, like if it is e to the power 80, then they just simply make it make your denominator is equal to 0. Always it will be greater than that particular values. So like as for example, if your function is e to the power 80, and then the Laplace transform will be 1 divided by s minus a, so the ROC will be the simply s greater than a. And two-sided, like if it is the function is e to the power a of modulus of t, means the function will be e to the power minus at and e to the power plus at. So in that case, the region of convergence will be lesser than a and greater than minus a, in between that. Here are the some properties of your ROC. So ROC is always a right half plane or a strip in a S plane always. And f of t is like if f of t is casual, g is for t greater than 0, then ROC of that form real S always greater than the particular values, that is sigma. And f of t is anti-casual, exists for t less than 0, the ROC will be the real part, that will be the lesser than the real part of that complex number, that is sigma. Similarly, you can check out some more properties. So ROC is simply, actually it will be like if you wanted to find out the ROC, then just make the denominator 0 and find out where your S will be defined. So wherever your S will be the valid, that is integrable for that particular function, so that will be called as the ROC. And so in the next class, next session, so we'll discuss the analysis of the LTI-CT system using the Laplace transform, and we'll see the some more problem using the Laplace, the transform properties. Like we'll see the, the time shifting, frequency shifting, the scalable, some different properties, and based on the some examples. Thank you for listening me. If you have any doubts, please drop your comments. Thank you.